Any API has a breaking point. A sudden traffic spike can overwhelm a server, exhausting memory and triggering a cascading failure across the network. To protect against resource exhaustion and deliberate abuse, systems rely on rate limiting as their primary defense mechanism. If you are running a single isolated server, tracking how many requests a user makes is a trivial computer science problem. You keep a simple counter in memory and increment it. But modern systems operate at a completely different scale. They handle millions of concurrent users whose traffic is routed through API gateways and distributed across hundreds of independent, load-balanced nodes. This creates a severe architectural tension. How do you maintain an accurate global count of a user's requests across all these independent servers without introducing network latency that cripples your performance? To solve this, we have to evaluate the mathematics behind the core rate-limiting algorithms and then design a production-grade distributed architecture capable of supporting them. A naive rate limiter in a distributed environment creates database bottlenecks and state fragmentation, taking your system down faster than the traffic itself. When controlling traffic volume, engineers typically start with memory-efficient bucket algorithms, specifically the token bucket and the leaky bucket. In this flowchart of the token bucket algorithm, a bucket with fixed capacity is continuously refilled. Requests consume tokens. If empty, they're discarded. Accumulating tokens during idle time builds a reserve, allowing the system to instantly absorb massive traffic bursts. This behavior is known as traffic policing. It enforces a long-term average rate while remaining inherently tolerant to the bursty nature of normal API traffic. The leaky bucket algorithm operates differently. It acts as a strictly bounded first-in, first-out queue. Incoming requests are processed at a rigid interval. If the queue is full when a new request arrives, it's immediately dropped. There is no capacity for bursts. This is called traffic shaping. It forces irregular, volatile input traffic into a perfectly uniform output cadence. Both bucket approaches are highly memory efficient. However, they measure overall volume and capacity. If your system requires strict, time-bound quotas, like exactly 100 requests per minute, bucket algorithms lack the necessary temporal precision. To enforce exact time-based quotas, we have to move to window algorithms. The naive fixed window counter divides a timeline into rigid, non-overlapping blocks. This introduces a vulnerability called the boundary burst. By sending 100 requests at 11:59:59 and another 100 at 12:01, a user bypasses the limit, forcing 200 requests through in just 2 seconds. To eliminate boundary bursts, the sliding window log continuously slides a fixed width bracket forward, dropping expired timestamps. When a new request arrives, the system prunes the old, counts what remains inside the bracket, and evaluates the limit. While this guarantees perfect fairness, the computational cost is severe. Storing exact timestamps requires O of n memory. During a massive traffic spike, this log grows exponentially, leading to rapid memory exhaustion and failure. The optimal hybrid approach is the sliding window counter. Instead of logging individual timestamps, this method tracks simple request totals for each minute. It then calculates a weighted mathematical average, combining the total from the previous window with the total from the current window, based on exactly how much time has elapsed. This approximation achieves near-perfect temporal accuracy, eliminating boundary bursts, while maintaining the constant O of 1 memory footprint necessary to operate at massive scale. In a load-balanced environment, a user's traffic is distributed across multiple application nodes. Rate-limiting logic cannot live in isolated server memory. The standard fix is to centralize the state, placing the quotas into a fast, in-memory data store like Redis. But a shared database introduces a fatal race condition. Imagine a user makes 2 concurrent requests routed to node A and node B simultaneously. Both nodes query Redis at the same millisecond. They both read that 1 token remains, and both approve the request. Both nodes then decrement their local value and write token 0 back to Redis. The system has just allowed 2 requests through when only 1 was mathematically permitted. In a highly concurrent distributed system, standard database read and write cycles guarantee state corruption, effectively bypassing the rate limit entirely. Solving this race condition requires absolute operational atomicity. We must bundle the read, evaluate, and write steps into a single, indivisible action. Distributed locks introduce too much latency. Instead, we shift the execution logic directly into the database itself, utilizing Redis server-side Lua scripting and its native sorted set data structure. Inside a single Lua script, Step 1, a zrem range by score command instantly purges outdated timestamps. Step 2, zcard counts the remaining active requests. Step 3, if under the threshold, zadd appends the new timestamp and returns an approval. Redis is single-threaded, executing Lua script synchronously. While this script runs, no other node in the network can interleave a read or write command. By combining Redis with Lua, we guarantee perfect, strict concurrency control without the massive latency overhead of traditional network locking mechanisms. Our architecture is now defined. Application servers handle the routing logic, but delegate state storage and atomic execution to a central Redis cluster to maintain accurate, high-performance quotas. Deploying this across a distributed cluster requires an engineering concession to the CAP theorem. We are prioritizing availability and partition tolerance over strict consistency. Because cluster data is sharded and replicated asynchronously, there is a fractional risk of state inconsistency if a primary node fails. For API uptime, this is a mathematically acceptable trade-off. However, as systems scale to globally distributed multi-region architectures, the cross-region network latency required to check a centralized Redis store becomes a hard bottleneck. Looking at this research abstract for a CRDT-based rate limiter, we can see the bleeding edge of the field. To eliminate cross-region latency entirely, engineers are abandoning centralized databases, shifting toward conflict-free replicated data types that rely on decentralized eventual consistency. Mastering rate limits requires understanding that there is no perfect algorithm. There is only a series of calculated compromises between memory efficiency, mathematical precision, and the limits of network latency.